These are solutions to another rotation problems worksheet that's called More Rotation Practice. We just need a lot of practice with these kinds of problems. It looks like some of these might be overlap with the other worksheet, and yet I think some of them are also different. So we'll just go through them as if we haven't seen them before. I know in the previous practice problems one, we did this particular problem. So maybe I'll skip that one. But I can barely make them out here because the scan is a little bad, but let's try to read it. Problem 1228. A uniform disk of mass m and radius r is supported vertically by a pivot at its center. As shown in figure 12.5, okay, so that looks like this particular one here. A small dense object, also of mass m, so this little rectangle here has the same mass as the mass of the entire disk, is attached to the rim and raised to the highest point above the center. The unstable system is released from rest there. And, of course, it's hard to balance it, so it starts spontaneously moving. What is the angular speed of the system when the attached object passes directly beneath the pivot? So it starts from rest, goes faster and faster and faster, and then we want to know at what is omega when that mass is on the bottom and it's zooming past the bottom. And I said here, if it helps, you can assume the mass is 3 kilograms and the radius is 0.5 meters since we're used to doing problems with more numbers in them. Okay, so this sounds like an energy methods problem. Oh, and I forgot to say, these are not in the right order, my solutions, but they're all down below. So we're looking at problem 1220 or 28 here. That is right down here. It looks like the very last solution. So this is an energy methods problem because we know at the very top the angular acceleration is 0, and then it gets bigger and bigger and bigger when that mass is out to the side, horizontal from the rotation axis. The alpha is maximum, and then it gets smaller and smaller as it goes down to the bottom. So alpha is not constant. We can't use kinematics to solve this because it's not a constant angular acceleration kind of motion. But we can use energy methods, and the first thing we're going to need to do is figure out the combined moment of inertia of the whole thing. And because if you have an object composed of a bunch of different bits of mass, you can always divide up the moment of inertia into the moment of inertia of this part of the object plus the moment of inertia of this other part of the object. And we're going to do that here. We're going to say the total moment of inertia of the combined object is the moment of inertia of the disk. We can get that from our table of moments of inertia, plus the moment of inertia of the mass that's on the outer rim with respect to the center. And we know if we have a little bit of mass and it's a distance r from the rotation axis, and in this case it's mass m and radius r, then its moment of inertia is just mr squared. That's what we added up to get the total moment of inertia. So the sum of those two are 1/2 mr squared plus mr squared is 3/2 mr squared, 1.125 kilogram meters per second, kilogram meters squared, if you use the numbers that I gave below the problem statement. Why do I need that? Because I'm going to take my system to be the disk plus the mass on the edge, together with Earth, where gravity is an internal force, and we'll take the pin force or whatever the pivot axis is, that the force it's exerting on the disk, to be an external force, but it doesn't do any work because that point at which it's being applied doesn't move. And the point at which a force is being applied has to move in order for the force to do work. So if we do the net work done by all external forces, that's 0, and that's equal to the change in kinetic energy plus the change in potential energy. And in this case, the kinetic energy just has the 1/2 I omega squared term in it, and that's because it's an object moving around rigidly around a fixed axis. You only have that other term, the 1/2 mv center mass squared term in there, if it's rotating around its axis while its center mass axis while the axis is moving. Here the axis isn't moving, so it's just 1/2 I omega squared. Starts out at rest. We want to know omega final and the center of mass. Well, let's see. How far does the center of mass move down by? Well, the disk itself, without the extra mass on it, its center of mass doesn't change at all. But the extra mass on the edge, which has mass m, moves down by a distance of 2 radii. So it goes down in y-coordinate by distance 2r. So the change in potential energy just by virtue of that piece that's actually moving from higher to lower is mg times minus 2r. And we can plug in the numbers and solve for omega final. If you take my number 7.23 radians per second as it's passing the lowest point. All right. 817. What power must a man expend on a 100-kilogram log that he is dragging down a hillside at a speed of 0.5 meters per second? The hillside makes an angle of 20 degrees with respect to the horizontal and has a coefficient of friction 0.9. This problem was actually relevant for our last exam. I guess in the term when I made this up, we hadn't done power until the third exam. So we can still talk about the solution, but it's not relevant for the upcoming exam. So that's problem 817 right here. So we're going to use the instantaneous power is the product, of Fx times Vx, right? That was our instantaneous power. We know the Vx, so the whole point is to find the force that the man has to pull parallel to the plane on the log width. What is that force? Well, we're going to get that by doing F net equals ma, and in this case, I think the man is pulling it at constant speed, so a is 0. All right, here's the free body diagram. The log right here, we've got a normal force, the force F that the man is pulling with, the kinetic friction force, and the weight force. Those are our forces. And as usual, we're going to take parallel and perpendicular to the plane to be our x and y axes. We're going to need that normal force because it comes into the x-coordinate. So let's first do F net y equals may, and ay is 0. And that allows us to solve for the normal force. Then we're going to use that in F net x equals max, and that's 0 also. It's moving at constant velocity. All the acceleration components are 0. And there are 3 components that are non-zero, that have non-zero x components. For my choice of axis, F has a positive x component, so does the weight force, and the kinetic friction force is negative. So here is F comes in with a plus sign, kinetic friction force, that's mu kinetic times the normal force, right there, and that's negative, and then the other positive one is the x component of the weight force, 100 times 9.8 times the sine of 20 degrees. Sum of those is 0, gives us F is 493.6 newtons, and then the power is Fx times Vx, 246.8 watts. Again, not relevant for our upcoming exam, but not bad practice. We need to remember that stuff for the final. Let's see. In the next one here, we're talking about figure 736. I think since I did this problem on one of the previous rotation practice problem worksheets, I'm not going to do it here. So let's skip this problem that goes along with this figure. It's in a previous worksheet that I've made videos for already. Okay, next problem, 959. A 4-gram bullet is fired horizontally with a certain initial speed into a 0.8 kilogram block of wood at rest on a table. Coefficient of friction between the block and the table is 0.3. How far will the block slide? What fraction of the bullet's energy is dissipated in the collision itself? Okay, so in this case, the bullet is coming to rest in the block, or at least it's fusing with the block, and then they move as a unit. Yes, so it's being fired into the block, and afterwards we have a combined object which has a mass of 0.804 kilograms, right? The mass of the block plus the mass of the bullet. How far does it slide? So our first goal is to figure out how fast the combined mass is moving just after the collision. And then the second problem is to figure out how far it slides, and then the third problem is to figure out the bullets and how much kinetic energy is lost in the collision itself. That's what's meant by that second part. 9.59. All right, so we're going to conserve momentum here from just before the collision to just after the collision. We'll call the direction everything's moving plus x. Before the collision, just the bullet has momentum, and then after the collision, we've got a combined mass object with an unknown v final. We can solve for v final. So if we wanted to calculate the fraction of kinetic energy that's lost, well, first of all, this first step is to find the kinetic energy that's lost, which is the initial kinetic energy minus the final kinetic energy. We just do that with 1/2 mv squared. So initially we just have the bullet moving, and then finally we have the combined objects moving. When we take that difference, we get 179.1 joules of kinetic energy that's lost. When people say, I probably wouldn't ask a question like this on an exam phrased this way, the fraction dissipated is the kinetic energy that's lost as a fraction of the initial kinetic energy. So in this case, take that kinetic energy that's lost divided by the initial kinetic energy of the bullet, and in this case, 99.5% of the kinetic energy is lost in that collision. Very inelastic collision. Most of the kinetic energy was lost. The other question we're supposed to answer is, once we've found that final velocity, how far does it slide? And in this case, one way to answer it, you could use energy methods. I guess I decided to use kinematics here. It's the forces are constant, and therefore it's slowing down with constant acceleration. So let's figure out what the x acceleration is by doing F net x equals max. And the only force being applied along the x direction, right, it has a normal force and a weight force, but if we call x the direction it's moving, the only force with an x component is the kinetic friction force, and that's a negative force. So here it is, mu kinetic times the normal force with a minus sign in front of it. And that's equal to ma. Remember, the mass of the object that's moving is 0.804 kilograms. Solve for a, and that a is constant all the way until it slides to rest. So we can use kinematics to figure out how far it moves. That's delta x. If we know its final velocity, that's 0. Its initial velocity, that's what we found its speed was just after the collision, 1.49 meters per second squared. Run that through the kinematics and we get it goes 0.378 meters. All right. Next problem, 1211. This corresponds to this particular figure up here, and we answered this question also in a previous video that I made. It was on a different worksheet that we did, so I'm going to skip that one about the stick right there. Problem 9.4. While waiting in his car at a stoplight, an 80-kilogram man and his car suddenly accelerated to a speed of 5 meters per second as the result of a rear-end collision. Assuming the time taken in this process is 0.3 seconds, find the impulse on the man and the average force exerted on him by the back seat of his car. So in this case, we can use the net x impulse is the change in x momentum if x is the direction that the man is moving. And so we can find the impulse delivered to him, and then we can calculate that impulse as average force times time. So that was problem 9.4. Problem 9.4. Are you in here? There it is. So impulse momentum theorem, if we call the direction the man is moving afterwards x, the change in momentum is, mass times final velocity minus mass times initial velocity. Initially he was at rest, so that gives 400 Newton seconds. And then we could say that impulse comes from some average force being exerted along the x direction, that's from the back of the seat, times the time that it took for that change in momentum to happen. That's 0.3 seconds. So dividing out the 0.3 from there, we get the average force is 1330 newtons. Next problem, 1041. A refrigerator with mass 100 kilograms measures 150 by 75 by 75 centimeters. How much force applied horizontally at the top edge of the front will make it start tipping backward? In other words, do you imagine being at the front of this refrigerator and you push horizontally straight back at the very top of your refrigerator straight backwards? If you push hard enough, you'll be able to get it to start tipping back on that back part touching the floor. What minimum force can you apply to do that? That's 1041, and that sounds like a static equilibrium problem. When, we can sort of think of normally, if you imagine, a little this refrigerator. So I'm imagining that in this case we're applying a force at the top corner, and we want to make it rotate around this particular axis down here. We're going to pull with a force and try to get it to tip toward us, I guess is the way the problem was phrased. And we could imagine there being a little foot pad right here at the bottom of the refrigerator, and one back here also at the back of the refrigerator too. And normally there are forces being applied from both of them, but at the point where it just starts tipping, this force on whatever the little foot is at the back of the refrigerator goes to zero. So just at the point where it's going to zero, it's still in equilibrium. In other words, it's not angularly accelerating. It's just starting to tip, or it's just about to start to tip. This force goes to zero up here. There's still a force on the axis. In other words, some of the weight of the refrigerator is being applied to the axis. But if we're calculating our torques with respect to the axis shown here, the part about which is going to tip, we don't need to include the torque. There is no torque due to the force that's being applied right at the location of the axis. So the important forces are the one we're applying. We're just going to call that magnitude F, and its moment arm is 1.5 meters. If you go back and look at the problem statement, that's the height of the refrigerator. Then we have the refrigerator, assuming it's a uniform block. Its weight force is as if it's being applied at its center of mass. So its weight is 100 kilograms times 9.8. And if the depth is 0.75 meters, then the moment arm for this force with respect to the axis is 0.75 divided by 2 to get that moment arm right there. Okay, so I'm putting in those two torques. If I take the positive direction to be counterclockwise, the one due to this force is positive, and the one due to this weight force is negative, and they add to zero. We can calculate what the required force is for it to be in static equilibrium, but I've just barely lifted that back corner off of there. If I pulled any harder, it would start angularly accelerating in that direction, but I'm just lifting hard enough to just barely get that back corner off of there. If I didn't pull it as hard, there would be some upward force from the floor at that back corner. All right, next problem. A car accelerates uniformly from rest to a speed of 15 meters per second in a time of 20 seconds. Find the angular acceleration of one of its wheels and the number of revolutions turned by a wheel in this process. The radius of the car wheel is 1/3 of a meter. It's hard to read that. 1120. So this sounds like a kinematics kind of problem. And in this case, we can figure out, just from the information that's given about the car's change in velocity is 15 meters per second, and that took 20 seconds. So the acceleration, average acceleration, but in this case it's moving with constant acceleration, so that's the instantaneous acceleration as well. Average acceleration is delta Vx over delta t. That gives 0.75 meters per second squared. Now, if that is the acceleration of the car, then that is also equal to the tangential acceleration at the edge of the wheel, so that we can figure out what the angular acceleration is in this case of the wheel. In other words, if we know the linear acceleration, we want to get the angular acceleration, we can use this relationship. Probably, I would say, if I were to explain this from scratch, not looking at this, what I would have done instead of explaining it this way, and maybe I'll say it in a slightly different way, I would have used V equals R omega. Remember, for rolling without slipping, we have V axis equals R omega. And doing that and getting the final axis velocity and the initial axis velocity, we can get the final omega and the initial omega of the wheels in that case. And then I could have gotten the angular acceleration by using kinematics. I would say omega final equals omega initial plus alpha times t, and that t is 20 seconds. Using those values, we could have gotten the alpha. So that's probably a less confusing way than the way I've explained it right here. But you got to get alpha first, and then we're going to use our constant alpha kinematics to figure out how many revolutions the wheels turn through in this process. And we're going to use theta versus t. We could also use the one that involves omega final squared and omega initial squared, but again, this is how I did it in this worksheet. So delta theta is equal to omega 0 times t. Initially it's at rest, so it's not rotating at all, plus 1/2 alpha t squared. So when I calculate that, that gives me an angle that it moves through in that time t of 450 radians. Then I change to angle units of revolutions by multiplying by 1 revolution is the same thing as 2 pi radians, so I'm multiplying by a factor of 1 there to give 71.6 revolutions. All right, and it looks like problem 1212 is a problem we also solved on a previous worksheet, so I think I'm going to stop the solutions there. It looked, there was a fair bit of overlap with this worksheet with the previous one, but there's a few good additional practice problems in it.